Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, welcome to the AI for Good webinar series from molecules to models, which features topics from several ALICE programs. And today we are pleased to welcome Gustavo Chamvas and Markus Reichstein, directors of the ALICE program Machine Learning for Earth and Climate Sciences. And this program brings together leading researchers to explore how AI can support understanding and action in response to some of our planet's most pressing environmental challenges. And together with Maria Piles and Joachim Denzler, Gustavo and Markus also curate the AI for Good webinar series, AI for Earth and Sustainability Science, which highlights cutting-edge developments at the intersection of AI, climate, and sustainability. And let me begin by introducing our first speaker, Gustavo Chamvas, and he's a full professor in electrical engineering at the Universidad de Valencia in Spain. And Gustavo leads the Image and Signal Processing Group, an interdisciplinary team of 40 researchers working at the interface of AI, Earth, and climate sciences. And he has coordinated and participated in over 60 research projects across academia and industry, and has also received numerous recognitions, including 2 ERC grants in different disciplines. And Gustavo is also an ALICE Fellow, the highest level of recognition in the ALICE network. And today's talk of Gustavo is titled AI for Earth and Climate, from Satellite Pixels to Causal Insights for Effective Action. Gustavo, the floor is yours.
Thanks very much, Conrad, for the nice introduction. Hello everyone. My name is Gustavo Camps. I'm coming from the Universidad de Valencia. And today I wanted to rather take you on a journey from satellite pixels to actionable insights. And my main goal here is to show how AI can empower climate science and sustainability. I will give you a bunch of examples, and also about, I will try to pick up some illustrative examples, showcase some successful stories, but also some pitfalls and some challenges that we will find in our pathway to a successful deployment and application of AI and sustainability sciences. So let's dive into this AI for Earth and climate. So we are basically concerned about this little nice and in principle humble and innocent object called Earth. And we are concerned about many different questions here. So what is the health status? What are the vital signs? Can we monitor the system? Can we predict its behavior, the future states? Can we, let's say, harvest all the possible information that we can collect to optimize some processes occurring on the Earth system? And also we can say something, can we say something or anything at all about the life in the planet? Can we do this, let's say, optimally in almost real time and ideally in an automatic manner? In summary, how can AI, for example, could be used for mitigation and adaptation to climate change? So these are very pressing questions, and as a clinician, we do the same as they do with the human body, with human system. No, so we want to do inferences about the complexity of the system, and respond to some pressure questions. And if we want to do inferences about this Earth's complex system, well, we basically measure and measure and measure again. So we use, for example, Earth observation data acquired by many platforms and all kind of sensory systems on the ground, but also many satellite sensors above our heads. But not only observational data collected by sensory systems, but we are now kind of living in this perfect storm where we have, on the one hand, massive EO data, Earth observation data, but also high resolution models that can resolve processes at an unprecedented detail. And in the middle of all this mass of big data sets, we are witnessing how AI can handle this wealth of data efficiently and find patterns and try to understand what are the complex processes that we are observing and try to explain, of course. Well, actually, AI can give us some, let's say, new lenses to view our planet and exploit all this information we get for impactful applications. And also, as we will see in the talk, as some actionable insights as well for mitigation and adaptation. We can now, for example, apply and deploy AI in many different fields. No, weather can be better predicted. We can, in principle, start picking some processes, so we can start seeing some successful stories of application of AI for predicting climate futures, also assess impacts, detect extremes, try to explain them, and also, of course, there are many applications on optimization of resources of all kinds. Let me just give you some simple examples in all Earth spheres. So from the biosphere to the atmosphere and the water parts as well. No? For example, we now use routinely satellite sensors to monitor crops and also understanding trying to understand what are the main drivers of success and failure of crop production. And this is actually key applications for food insecurity, for food security. For example, we can now derive like explicit maps like the one that you have in the slide for crop health, status, water stress, production, etc. And we can anticipate this with this nice combination of exploiting regularities in spatial temporal data acquired by satellite sensors and simulations, together with in situ data and the combination of both through the AI mechanisms that can actually infer these quantities from the observational data. Right? Beyond land, AI also helps monitor water bodies and oceans. It can, for example, estimate organic carbon or predict coastal sea level change. And also, let's say that all these quantities, all these variables that we are really interested in capturing and monitoring and forecasting, they are crucial for marine sustainability. These are not just academic exercises, right? But they are really supporting nowadays like real world planning and resilience strategies. From cloud detection to methane emissions, AI also improves how we analyze atmospheric conditions, which have high implications, for example, in population health, but also implications in climate. No? So cloud parameterization, for example, is one of these important aspects of the climate modeling, where climate modeling community is actually struggling because it's one of the big chunks of uncertainty that we are not able to account in climate models. We have now relevant AI-guided applications in place, for example, like identifying methane's hotspots from space. And this is, as I said before, crucial for climate mitigation. Now we also find machine learning on board those satellite sensors, and they provide real-time information, for example, in post-catastrophe management and assessment, like in flood mapping that you see in this very nice example in this paper. In the last few years, it goes without saying that we are witnessing the AI revolution in weather forecasting, for example. Now models are accurate, but also not only for the sake of accuracy, but also because they are now much faster than traditionally physics-based models. And this has like nice implications because it allows us kind of democratization of the forecast. So, and also, of course, deployment of many applications, informing stakeholders and governments in a more timely manner. by 2050, like it is estimated that 70% of the world's population will be urban. And maybe we can remember what Shakespeare said a long time ago. He said something like, "What's the city but the people?" So we should kind of do our best to monitor what is happening in urban environments, and if we can optimize resources there. No? And actually, in this current scenario of climate change, this is actually calling for a definite action for mitigation and adaptation. So we want to use and deploy AI systems to contribute to more livable cities. And let me just give you a bunch of examples where this is already happening, even if it is in its infancy. So, for example, mitigation of greenhouse gas emissions requires important changes. Important changes in many aspects, right? Like in electricity systems, in transportation, in buildings, in industry, in the land use, etc. No? Here it is just like a tiny example where AI can help map solar panels and green roofs and sustainable cities. So this is kind of a roofpedia, so where urban planning is actually AI guided. So this is interesting because it is not only kind of optimizing the resources and the mitigation and the emissions, but also, you know, it can be used for something else, like optimizing energy consumption, monitoring emissions, etc. No? And this is, of course, the main goal of this sort of strategies. They have to do with, you know, designing climate resilient infrastructures in the world. But this is just an example. Let me just give you a bunch of more in the urban environments. So targeting SDG 11. So adaptation is also crucial, you know, and that requires, of course, planning for resilience and disaster management. And deep learning is actually, you know, in place and in many different applications. So as I've said before, weather models are optimized to track the rapid, let's say, chaotic changes of the atmosphere. And deep learning has really recently impacted in these associated problems. Other researchers have tried, as you have seen in this slide, tried to translate, let's say, high resolution climate forecasting to risk scenarios, right? Like, for example, localizing flooding patterns, as we have seen before. And as well, also as, you know, deploying deep learning models to improve or alleviate, like, or help in a kind of an effective disaster response. Later, probably Marcus will talk more about these particular applications. But also AI can reveal patterns, for example, of wealth of human activity from space, right? So using all the wealth of observational data, we can estimate, for example, energy consumption, potential of plausible regions where conflict is actually occurring, because you can actually capture some features that are associated to this human or anthroposphere, biosphere interplay processes, right? So, for example, urban structure can hint at poverty or wealth using this high resolution imagery with machine learning, or, for example, it is worth mentioning this NASA black marble maps of energy use, disaster impact, light pollution, and many more. All of them, they're basically capturing in some sense of important drivers that explain us what is the status of the Earth and what are the important aspects to act on. So far, so good. It looks like AI in combination with a big amount of data, that's the solution to all our problems. But is everything possible, and is everything like solvable with just this little and simple recipe? Well, not quite. AI is not magic. It's not a silver bullet. The vast majority of deep learning models do not respect, for example, the most elementary laws of physics, like the mass or energy conservation. It has also been argued that deep learning models just fit. They actually work very well at that, but yeah, nothing fundamental is actually learned. Actually, these models are becoming bigger and bigger and bigger with more parameters, billions of parameters, like in large network models, for example. And it is really complicated to sense what are the internal mechanisms why these models do predictions or take a decision or whatever, right? And finally, even if these models actually capture some sense out of the data or some relationships between input and output, how can we be really sure that they capture something or some sense of causality or causal relations between the data? Well, these are tough questions, and this, in my opinion, is calling for an integrated agenda where basically we want to push like three main aspects of first, physics-aware machine learning, how to incorporate this physics or domain knowledge into machine learning, how to unveil what is the knowledge encoded in AI, and also, of course, we want to discover and to estimate effects in costly terms, right? So in a nutshell, we want to both encode knowledge and decode knowledge through this AI-guided research, right? So let's unpack this, and I will give you a bunch of examples again about every single step here in these challenges and eventual solutions. So in physics-aware machine learning, we want just basically to move from this purely data-driven approach where you want to learn a function f out of x equals y, to a little bit more complicated one where basically you incorporate some domain knowledge in the form of equations or domain aspects or ancillary data that should be relevant to the problem at hand or whatever. And then you want to do exactly the same exercise. So improving prediction, but at the same time you want to be consistent with the prior knowledge or with the equations and the laws that should be actually governing this system. So we want to live in this, let's say, interplay between machine learning and physics. And for that, we want to exploit, as I said, domain knowledge, ancillary data, rules, differential or partial differential equations, etc. Yeah, in this particular little paper, we try to organize all the field in these four different families of approaches where machine learning and physics interact. Well, for example, we have like algorithms that can blend data and model simulations together. We also have methods that approximate costly relative transform models with machine learning. We also have methods that learn, let's say, the input state or the parameters of the system from observational data. So that has to do with improving both forward and inverse modeling. But also we want to, and there are methods that can actually interact with the data and learn some equations out of it, right? This is the field of learning physics or equation discovery. So I will give you a little example for each one of them. Let's start with the first one, which we call it hybrid modeling. It has many names in the community, and every researcher calls it in different manner. But essentially, the idea here is try to encode or incorporate prior knowledge inside the machine learning model. You can do it also in the loss function, but here, for example, we're interested in incorporating in the very same architecture of the deep learning. For example, on the left-hand side, you have a general framework to, let's say, in quotes, physicize deep learning model by including some constraints in the network layers itself. So you basically design the physical model parameters layer or layers. And then you want to enforce, let's say, that the output should not be just a data-driven output, but also a physically driven output as well. No? So you are basically fueling all the processes of the previous layers through the physical model parameters, and then you basically provide this physical output predictions. On the right-hand side, you see a particular example, right, where a deep learning model is then physicized to learn motion fields that are not only accurate, as they typically are, or by using just data, observational data or simulation, but also physically consistent. And for that, we basically, or the authors here, included an extra layer that basically warps. So this is a warping layer, let's call it like that. That warps the motion field estimates with a physical model. And the nice thing of the current implementations is that you can learn all these end-to-end. So you can optimize all the structure, all the architecture end-to-end, so you can learn the parameters of the model. And eventually you could even learn parameters of a physical working model as well. The second family of methods have to do with acceleration, with emulation or surrogate modeling. Again, it depends on the family or the community that you're addressing to. You will find different terms: emulation, surrogate modeling, approximate modeling, etc. Right? So here, for example, we use machine learning models that can provide you like a replacement of a very costly, complex code of a physical model, right? So you gain, of course, speed, because once that it is trained, the inference time, machine learning is typically very fast, much faster than a physical model for running simulations. But at the same time, it provides you some advantages, because the model can actually be more mathematically tractable than in terms of you can, for example, derive confidence intervals if you're using a Bayesian deep learning or Gaussian process for the emulation, etc. Right? And what is interesting is if you look at the figures on the right, you can actually hardly differentiate the rankings of, for example, of different spectral channels obtained with the original model and with the emulators. Here on the right, you have 3 emulators and the true RTM rankings. So it is really hard to differentiate. So that means that the emulator themselves have encapsulated some physics pretty nicely and efficiently overall, no? Because it is just running at a fraction of the time. When it comes to learning parameterizations, we do that very often, not only in remote sensing and Earth observation, but also in climate sciences. You want to infer some parameters from some observational data, right? So here is that it's basically and typically and traditionally framed in this context of forward and inverse modeling. And here we work with variational inference because it was quite convenient. So basically, we try to face this problem of learning parameterization of variables y from observational data x. And basically, the model just gives like a Gaussian likelihood, and we assumed a Gaussian prior. And we wanted to fit or learn the prior parameters. The problem is that if you want to integrate these RTM, these relative transfer models, it's a very complex model. It's very costly, it's very complex. And then if you put the RTM inside the Gaussian mean, the solution is really tough. So that's why we resolved to using variational inference. And with this framework, we were kind of able to learn the prior distribution of several land parameters, like canopy water content, chlorophyll, and dry matter, something that was not available because you don't have these actual measures explicitly, but you can simulate those with RTMs. And of course, at a fraction of the time, you not only have the emulator, but you also have the retrieval algorithm, so you can actually estimate these parameters very, very quickly. Okay, so far so good, but then we can develop also machine learning models that can incorporate physics constraint and learn parameterizations and this and that. But still, we are working with complicated and big monsters, big machine learning models, that are hardly interpretable. The question here is, what did we learn by doing this process, or what did the models actually learn? So this has to do with this area of machine learning called explainable AI. And there are several approaches. Well, not several, but many, tons of them. There are many algorithms, and they can be grouped in different families of explainable AI methods, from sensitivity analysis to decomposition, to inversion and optimization, distillation, activation, visualization, etc. Right? So there are many, many different methods. Let me just give you an example here. We used here a multi-scale and multi-branch variational autoencoder to learn the latent representation, and this was meant to be for heat wave detection. So the encoder just basically ingests the spatial temporal cubes of many variables, actually 8 variables: surface moisture, result moisture, GPP, transpiration, air temperature, over several years, weekly sample, etc. And then you learn a representation, a latent representation that then you can sample from, and then you can also, of course, Gaussianize it and use that as a kind of an anomaly score. The bottom on the left, you see a detection map that basically captures some sense of the anomalies here in 2010 that was due in this particular region. You see there that In orange, it is the boundary of what it is well known as the Russian heat wave in 2010. But more than just detecting this event, this heat wave, and the impact that it had there in vegetation, for example, you could try to explain what is going on inside this encoder, the coder, right? So you look at the encoder, and then we apply our regular explainable AI technique called integrated gradients. And in these integrated gradients, you can actually put numbers to what are the main variables impacting the decision of the anomaly score through time, right? It is important to note here that the encoder-decoder is an unsupervised method here. So we are learning just purely from data, and we want you to, and also the notion of anomaly is quite elusive. So you have to take this with a grain or two of salt. So here, it basically said that, the explainable AI method could not only point to temperature anomalies, you see where the variables are in red, but also some water, or let's say moisture deficit some months before as a kind of a potential driver of the drought or the heat wave. So this can help, it can help us to focus on the right variables to monitor, not just to assess what just happened or what just the algorithm or the model learned. Here, I want to show you a little bit of another use of explainable AI with another method, very popular, which is SHAP values, or SHAP. And here, the problem becomes more articulated, more complex, because we are now dealing with both, not only environmental, but also social and economical variables. Here we are working with migrations, people migrations, and the migrations due to several hazards, the most important ones, like floods, like landslides, like storms. And this was, a collective effort to capture all kinds of data. And then we run causal forest and different machine learning algorithms for predicting well these let's say internal displacement or migration of people. And interestingly, the explainable AI models could also identify this kind of differential vulnerability. You see the figure on the bottom on the right. And this actually patterns is interesting because just by doing regular machine learning plus explainability kind of captures that there are some thresholds on income that combined with the severity of the hazard lead to completely different patterns of migration. So it can explain that there's different groups of people that are vulnerable in different circumstances, and the wealth is basically one of the key aspects separating the vulnerability of the population or the risk of population displacement. No? This is important because it not only allows us to gain some trust in the models, because you see that there is something meaningful inside going on, but also because it allows us to perform more kind of informed decision making, right? So identifying this vulnerable population, guiding resource allocation, for example, in management of disasters, and also shaping kind of the target adaptation strategies that they should be in place. Okay, let's move on for the third, let's say, challenge in our arena, which is explaining deep learning models. It is clear that it is not explaining the world, right? It is not explaining nature. So we can answer questions of what, but not really of what if and what will have happened if. And this is the field of causality. And so far, there are many tools of causality, but what I wanted to stress here is that basically this area of disaster management and preparedness, etc., they involve answering causal questions and to identify the proper drivers of disaster, not just the patterns, but the drivers. No? And they should be causal. This will help us not only to explain what just happened, but also try to mitigate what are the potential impacts. Because in the models world, the causal models world, maybe eventually you can start doing counterfactuals and analysis of cause effects estimation. Right? For example, here, what are the real causes that of people just forced to move during a drought, for example? And or causal AI can help us? Well, now there are many works out there that promise like causality for solving this type of problems. Of course, there are many challenges and many problems in our pathway. pathway, not only data challenges, but also model challenges, and of course assumptions, something that we have to deal with in causality. Let me just showcase this causality on human displacement. Disasters associated to weather extremes and climate change impact migrations. That's clear. Millions of people are forced to migrate. And in this recent paper, it was argued that quantitative attribution, for example, is a very, very complicated one, very complex problem. It does not only involve environmental, but also conflicts, context, cultural traits, etc. And the authors here in this paper advocated for more quantitative assessment of the migration problem. We did follow this in order to mitigate or try to alleviate these problems in SDG 2 and 10. And here, basically, we collected all kinds of data. You can see here food prices, livestock prices, water prices, etc. In the Horn of Africa that suffered many severe droughts and heat waves in the last decade. And we work at the district level. From this time series for the last decade, we were able to learn some causal graph with a method called PCMCI. You can not actually apply the method directly for structural learning, but you have to control for confounders. You have to blacklist some unreasonable links, and also test many time lags and legacy effects, etc. So it is kind of I would say almost an artisan work, of course, aided by the help of these causal discovery methods, but still it's a challenging one, right? So from this observational data, we were able to derive this kind of causal graph. After discussion with the experts in the field, the humanitarian sector, they said, okay, it kind of plausible. So here, the model was able to learn this causal graph of relationship, the strength of the relations, and the time lags also associated to each interaction between cause and effect. That's the number that you see on the edges. And basically, if you focus on the drought ADP, so the drought-induced internal displaced population, so the amount of people that is forced to leave because of whatever else, basically, most of the variables that are actually directly impacting on drought ADP are water and food prices, mainly also driven by SPI, so precipitation. Right? So you can say something about the system, right? So you can learn about what are the strength of the drivers, but also the lags, right? So we wanted to optimize all this problem of causal discovery, and that's why we created some years ago COSME. If you go to cosme.net, and you will be able to upload some time series, and then if you are skilled in the different algorithms that are implemented there, you can start playing around with the other parameters, and then schedule a job, right? And then if you are not that skilled, you can leave just the machine to do it for you, and it will run. Of course, you will have to wait some time. It is running on our servers, and in the end, it will just give you some causal graphs that you can manipulate, also play around with the thresholds of significant tests. And then if you're also interested in identifying what are the main or the parents of a particular target variable, then you can go for this hierarchical edge boundary, right? We recently connected it to ChatGPT, and that can create narratives for you from the, let's say, from the data-driven causal graph that you discover, right? With whatever causal discovery method here. So now this is becoming very interesting, especially for practitioners that they don't want to learn too much about causality, but they want to scrutinize what are the solutions, and that kind of facilitates the tasks. So as a conclusion, I would like just to wrap up saying that the future of climate resilience lies in basically understanding our planet, not just predicting it. The current models are basically seldom explainable and interpretable, and one can be right for the wrong reasons, and also, purely data-driven models can actually identify some nonsensical relationships, not only physically nonsensical, but also causally implausible. And this is why we should aim for AI that it is not just accurate, but physically consistent and causal. And fitting, of course, is not enough. And that's why I always say that give physics, shy, and causality a chance. Thank you very much.
Yeah, thank you very much, Gustav. And before we go to the Q&A, I would like to introduce our second speaker, Markus Reichstein. Markus is director at the Max Planck Institute for Biogeochemistry in Jena and professor for global ecology at the University of Jena. And he is passionate about combining systems thinking with data-driven approaches and AI to address complex challenges at the climate, environment, society interface, all with the goal of helping societies become more resilient and sustainable. And Markus is an Alice Fellow and also co-lead founder of the Alice Unit Jena, together with Joachim Denzler from the University of Jena. And Markus' talk today is titled Learning the Earth, from Understanding Processes to Early Warning of Climate Extreme Impacts with AI. And Markus, the floor is yours.
Yes, thank you for the introduction. Let me share my screen. Okay. Takes a while, but now you should be seeing it, right? Yes, so I will give different perspective on a very similar topic. Gustav and I, we talk almost each week about these things. So you will probably hear a little bit more on Earth science perspective on that team, and yeah, I hope you find it still complementary to what you have just heard from Gustav. Anyway, so if we talk about the Earth as a scientific object here, this is the Earth system, and it is such a fascinating system because it is complex. So complex systems where several spheres interact with each other. There are biological, chemical, and physical processes that interact together. And from a science perspective, Gustav also mentioned the importance of understanding causality is actually that it's a unique system. So we need to infer causality from observations or from models that we build from first principles, but there's no way to have experiments of multiple Earths basically. And that's why we also want to have these digital twins actually, so that we have digital pictures of the Earth, so that we can then do experiments with that and understand what interventions are. So this is kind of a new term, no? This digital twin, but in fact, actually, people have been striven for that for a long time, actually, and this is kind of called Earth system modeling, and and this approach was a little bit, what I say, it's a reductionistic approach, wiring everything together. So basically saying, well, the Earth system is a system of subsystems. We have here, for example, I mean, you don't need to read everything. We have the physical climate system, so the exchange of energy between here the atmosphere on top, the ocean and the land. And then we have more the biogeochemical system with the carbon cycle and nitrogen and nutrient cycles in general. Again, between the atmosphere, that's an atmospheric chemistry, the terrestrial ecosystems, and the marine system. So whether you see it's kind of a system of subsystems, and then each subsystem maybe is again consisting of subsystems, where at some point you can then say, okay, you can describe it with causal relationships that you get from lab experiments or from first principle out of physics or biology, although with biology it's a little bit more difficult with the first principles, as we all know. And since this program or this series is called From Molecules to Model, and I'm from the MPI for biogeochemistry, I couldn't help to insert this slide, but it will just show also a little bit that kind of reductionistic approach, if you want. Because if you talk about biogeochemistry, it's basically the metabolism of the Earth, and it's the role of molecules and atoms that are kind of transformed and transported in the Earth. And they all play quite important roles in the Earth. For example, they are carrier of free energy. So if there are a lot of chemists here, they will understand it immediately. Here we have ATP, so the ubiquitous carrier of energy in almost all cells. Or glucose, more like a storage of energy, where you can already see it's a very carbon rich molecule. But that's not the only role of biogeochemistry of molecules. It's actually much more diverse. They are carriers of physical-chemical properties, like CO2 you see here on the right-hand side is a carrier of absorptivity. So it absorbs long-wave radiation, causing the greenhouse effect, together with other molecules too. But it's also a carrier of acidity. So if CO2 dissolves in water, you all know that, then we have carbonic acid. And this leads, for example, to ocean acidification if it's more and more CO2 in the atmosphere. And then you see other molecules. I won't go into the detail here, but also that also have properties. And then they are also carrier of information, actually, like our DNA. Everyone knows this. Maybe the upper right, this octane all. Fewer people will know what this actually is. So that's kind of a carrier of olfactoric information, basically telling us humans, but also animals, that there are mushrooms in the forest. And that's actually quite important for communication in ecosystems too. Then we have a couple of molecules that actually are relevant for both spheres, like isoprene, very important carrier of atmospheric chemistry properties, but at the same time, it's also a carrier of information for plants, or methane, both a carrier of free energy, both for microbes and for us humans, still an important energy source, a gas basically. But it's also a carrier of absorptivity in particular, where this is a very potent greenhouse gas. So this is also quite important to be reduced, as we all know. And then there's one molecule missing. I don't know if you're guessing which one it is. It's water, actually. So water is really like in the Earth system, a unifying or kind of a molecule that's really important for all processes. And we have learned this lesson actually over the past decades, even if our institute was founded for the carbon cycle. And so this is basically just showing a little bit, okay, these are all, we can model all of those, and these molecules interact with each other. They interact in living organisms and so on and so forth. But you can also imagine that it's quite complex at the end. And so this paradigm of complex system modeling has been actually quite successful, in particular for atmospheric modeling. Here's an example of our colleagues in Hamburg from the MPI for meteorology, where they basically said, well, a couple of years ago, well, we can actually now resolve most processes in the atmosphere so that our simulated Earth looks like the real Earth. So I guess you cannot distinguish the left or the right, which one is the real and which one is a simulated. And it's because of high resolution modeling of Navier-Stokes, basically, and of course other physical processes in the atmosphere. So the clouds that you see here in white are kind of realistically, even if not exactly, but in terms of distribution, a spatial distribution realistically modeled. So so I really want to say that this paradigm has been certainly successful in many ways. But now if we include long-term climate dynamics, like the carbon cycle, then it's the picture, and that's where I'm coming from, the picture actually is partly a bit different. You may know that currently less than 50% of our emissions stay in the atmosphere, and there's a little bit more than a quarter taken up by ecosystems on land, and a little bit less than a quarter being taken up by oceans. So currently we are basically are lucky that those systems mitigate our emissions by taking up and absorbing the carbon. But it's not entirely clear how this will continue in the future, because there are different feedbacks, like if the Amazon is dying and so on, then carbon dioxide is released, or if the permafrost is melting, and so on and so forth. And now one can ask, okay, what do these Earth system models that rely on this reductionistic paradigm, what do they actually predict? And as you can see here, without again going into too much detail, but what you can basically see and take home is that some of them say, yes, the land uptake will continue until the end of the century. Others say, no, it will actually reverse by mid-century or so and come into negative uptake. So that means additional release. So instead of having a negative feedback, there will be positive feedback according to those models. So acceleration of the global warming, basically. So this has been published 2006, then 2014, and if you look into the current climate models, the picture has actually not changed. There's actually a paper from 2024 showing still the same picture. So this is of course very, very critical, let's say, from a scientific point of view, that we even cannot predict the sign of the uptake or the sign of the feedback. Just the next 100 years. And this has actually led to a crisis in Earth system modeling and has revisited. And our point is already also now, of course, now 5 years ago, our point was actually that insufficient use of data and observations has led partly to this crisis. So this was this perspective paper where we basically say we should harness data, we should harness the methods to extract information from data, deep learning, but combine it with process understanding in a data-driven system science paradigm. Well, and this is basically the point that we also wanted to make actually to machine learners is that, and to data science, is that Earth data is actually prototypical for big data with all the different characteristics of big data totally matched, and maybe in particular very strongly match a variety of data that we have on Earth, from point observations that are time series to Earth observation from remote sensing that give you pictures every day of the whole Earth, or more integrated observations in the atmosphere that are and we measure states and fluxes. So really different data. It's a kind of multimodal observation systems that we actually have on the Earth, and which makes the whole thing quite exciting. So just to be a little bit less abstract, a few pictures. The way you can see it basically. So here we have, for example, a Sentinel-2 image of the Lake of Geneva. 20-meter resolution. You see the detail even on the lake with the currents or the eddies in the lake, but also the landscape heterogeneity around it. And this is not just a single snapshot, but these kind of images are acquired several times a week. And okay, now my computer is frozen. I hope it's not for you. Okay, now we have the next picture. And with Sentinel-3, for example, okay, now it's slow. We can, the ESA could, for example, observe how a drought in Europe has been turning the vegetation from green to brown within a month. I don't know now. The animation is stopped in my computer. Okay, sorry, there's a bit of an issue. Okay, sorry. So the point is that we have, of course, we have multiple observations or temporal sequences of observations, which are akin to, for example, videos in classical computer vision approaches. Can anyone give me a sign if I can be still here, because my computer is kind of spinning and it seems that I'm not really online.
Yeah, we can hear you, but the slides looks like frozen or something.
Yeah, okay, thank you. Yeah, that looks like maybe I stop the sharing and share. Okay, sorry for that. I don't know what this hiccup is. And I should also speed up, I guess. I'm talking too much.
Yeah, thank you, Markus, for your presentation.
No,
And
I
are
was
you
not finished, no?
not finished?
No. Can you see it?
Yes.
Yeah, I don't know. Yeah, so I don't know, but it's okay. The PowerPoint is still frozen, it seems. No, I wasn't finished. Right, we started also, I think, only more or less 12 minutes ago. But if you have a strict deadline, we could, of course, I could be very fast. But at the moment, I bet the PowerPoint has crashed. Sorry, that's my problem. Yeah. Wow. Yeah, I don't know what's happening here. It's not responding. Okay. Yeah, but maybe what we can do also to save a little bit of time then. Um, okay. Sorry. Now recovering PowerPoint. Oh. Okay, now the PowerPoint is running again, I think. Mm. Yeah. Okay. So I think now we are back on the on the presentation. There's a little bit of the question, of course, what we if we can go over time a bit, like 10 minutes, then probably I can try to finish within 10 minutes or so. Then we have 5 to 10 minutes for questions. Yeah, so basically what I was saying basically with the Earth observation, we have a lot of data and observations of how the Earth actually looks like. You could see it in the slides before, but not necessarily what they do. So it's basically something about the structure that we see versus the function that the ecosystem is doing. And that's, I think, actually a very interesting challenge, because we need to translate what we see with a function, basically into what the ecosystems do. And there are latent unobserved states involved and so on, which relate very strongly to many machine learning problems. And we have been addressing this for a while with ground observations, which are basically distributed between the Earth. You can see here the molecules CO2 and water are kind of moving through the system, and that is kind of measured so that we get the flux density between the ecosystems and the atmosphere. And this then leads to these kind of direct observations of what the ecosystems are doing. In this case, how much carbon dioxide are they taking up? This can be interpreted or shown in these kind of so-called fingerprints. X is time of the day, Y is time of the year, and then you can basically see how different these ecosystems dynamics is. For example, tropical rainforest is active all year around, as you see, the green line is going through the whole year, while a beach forest, for example, starts very abruptly end of April, so soon here in Central Europe, and then will be also very, very active, but then stops again in October. That's why the system is not as productive as a tropical rainforest because of the winter, and so on and so forth. I don't go into more detail here. This actually method has been so successful, has been kind of a global network of flux sites. FluxNet has been established. And now the question is, how do we get basically from these individual points, like 500 sites or so, to a global picture? They are not equally distributed, so one cannot just do geostatistical averaging or so. But rather the idea is that we use this information that is available on the kilometer scale, use it together with Earth observation that I showed before, which gives us pictures of the whole Earth, but not the variables of interest. But at the intersection of these two scales that you see there, we can basically then build models, machine learning-based models that can predict what the ecosystems are doing based on how they look like. To simplify that, and then the model can be applied globally, and we get a very global picture. And back in the days, that's where we had kind of these first really data-driven estimates that are about, in this case, about CO2 uptake and release. And since this method is not only measuring CO2 fluxes, but also heat and water fluxes, we basically get multiple. Okay, now the system crashed again. No, I don't know what's going on here. My computer's okay. Nah, technically it doesn't work so well. I will try now. Okay, now we are here. Yeah, okay, let me skip this through. I don't know, it's really a bit annoying. Let me skip this also, just in the interest of time. I think it's would be so maybe I just make this summary. So basically, the interesting thing is actually that when we wrote that back in 2019, it was kind of a little bit forward-looking that we should really use deep learning for Earth system science. Now it's state of the art. So now basically everyone knows that we can use these things, and there have been so many successful approaches, so one doesn't need to show the slide anymore, but rather one should now talk about major challenges. And challenges are really generalizations on the one hand, out of distribution prediction in space and time, but also related to tasks. Then the learning the effects of interventions. Gustav already talked nicely about it. That's basically causal modeling. And then Earth science, we have often the space for time paradigm that we can infer temporal variation from spatial variation. That's needed when we only have short time series for some sensors, for example. But it's a question if one can really do it. Then the integration of variety across time and space scales, multimodality. Foundation models are really multimodal. Foundation models are certainly a very promising approach with self-supervised learning. And then we data-centric approaches that really respect kind of the properties of the data that are not always Gaussian and so on and so forth. And last but not least, I think another major challenge is not my field of research, was really ethics. With early warning, we really need fairness, accountability, transparency, and also safety if we talk about personal data. I really would like to advertise and highlight this paper by Esther Rolf that actually presents these challenges very, very nicely, and also some solutions. think on top of that, there is this learning of interventions effect that's not so much covered in that paper. And we can also be short on the next theme, because I think Gustavo also mentioned quickly the hybrid modeling, and I maybe give it only broad point here. So I think addressing some of these challenges really means we shouldn't throw the theoretical knowledge and domain knowledge that we have. So on the one hand, we have theoretical knowledge, we can ingest that into machine learning, then we end up with hybrid modeling. But I think on the other hand, the knowledge should be also is also extracted in data that we are maybe have been not thinking about before. And that's why multi-model foundation models might be very, very interesting if they are combined with causal representation learning. So the hybrid modeling, Gustav showed that already. I skipped this for this reason. There was just another example. I give you one example, one use case or case study example for the hydrological model, because it's such a it's easy to understand actually. So hydrological model is basically on the Earth. It's just moving water around on the Earth, no? And there's, for example, here it's usually ODEs or well, PDEs, it depends, but I formulated here as an ODE. For example, the change in groundwater is basically mass balance. So how much is basically extracted? QB is a base flow. How much is recharged into the groundwater, and how much is kind of flowing in a fast way into the groundwater? And then the recharge to the groundwater is is basically some coefficient that partitions the precipitation and the snow melt that we have into how much is flowing into the groundwater, how much is going into the soil, and how much is running off. And this coefficient is, so these equations are very clear. This is mass balance. It needs to be obeyed, but the coefficient is very hard to extract, or to extract from first principles. And so the idea is basically that here on the bottom, we have this hydrological model. I hope you can grasp it. It's basically this ODE for the groundwater that is kind of implemented with some plus and minus, so subtraction, and additions of the state variable and other variables too, like soil moisture. But then there are these partitioning coefficients that are derived or estimated end to end, or here in this case with a recurrent neural network. So basically the ODEs, some part of the ODE, the coefficients are kind of estimated with a machine learning approach, so kind of this combination end to end of a deep learning architecture with hydrological mass balance equations, and which are kind of differential equations. This actually, worked quite well. And with this, we can also infer then variables of the physical model, which are then informed with which are informed by the data and with a machine learning approach. Here, for example, on the lower part, we see groundwater storage, what is predicted or hypothesized by the model, or the soil water deficit hypothesized by the model. And this have been there have been no observations on those. So observations have been on evapotranspiration, runoff, snow water equivalent, and the total water storage. That are the observables. So my last point is that we can actually improve forecasts, we can infer latent variables and so on, but I would really advocate a more integrated approach, even if we go for societally relevant things. And Gustavo again also alluded to that already. And my point here is a good forecast isn't a good warning necessarily. If we look at an early warning chain, yes, it depends on, for example, weather forecast. But then we also need to have a hazard forecast. We need to understand what is the likely impact. So we need to have environmental modeling, socioeconomic modeling. But then even this is not enough. So even if you have a good forecast, but you don't communicate it well, you don't have a good warning and a good decision, then actually all was kind of in vain. And we have too many examples actually in the past, including in Germany, the Ahrtal flood, for example, where actually this early warning chain broke at one of the bridges. So we have prediction tasks and information tasks. Prediction tasks, even for weather, as you all know, machine learning plays now an important role. I think it's even more important for these more complex and hard to model dynamics that are hard to model from physical first principles, but one can do it again with machine learning. So there are promising examples. And for the information, also the information is really with generative AI, both language but also images. The hope is actually that we can generate better warnings that are more intuitive than just a abstract number like 200 millimeters of rain. For example, here in the upper right corner, an image is generated that shows how, with a flooding, your property might look like, and this can then activate people, hopefully in a more meaningful way, basically. Yes, I think this is more or less what I wanted to bring about. Maybe the last point is really, I mentioned it also before, to bring these different elements of the early warning chain together. Probably on the one hand, we need well-trained models that can be tuned very well. So it's foundation models on metrology, on geospatial aspects. The question is actually if we need one big one or if we need partly one and that are coupled. I think that's actually a research question. But what is really also important that and I think that's also really an open research point, that we need a representation learning that includes causal constraints, because otherwise also in the foundation models, there can be a lot of spurious things learned, and the features that are extracted might be not necessarily the ones that also are the right ones, for example, under distribution shift. Okay, but I think it's really an open research question here. So my final slide is basically, again, a depiction of the complex Earth system with the feedbacks and the big challenges that we need to address here in this field to make progress towards sustainable development under the kind of condition of more extremes and climate change, which clearly is a distribution shift. Thanks, and sorry for these kind of technical hiccups.
Yeah, thank you, Markus. And I would like to open the floor for discussions and start with the first question. You emphasizes the need for integrating physics with AI for climate modeling. How do we balance the flexibility of deep learning models with the rigidity of physical laws without sacrificing performance? I think this is addressed to Gustav.
Yes. Yeah, the question basically asks about, first, what do we gain, right, by including physics in data-driven models, and then if we gain something, can we be sure about that? And it is always the case. So, well, one of the hopes on this hybrid modeling approaches is that by incorporating physics, you will be able to incorporate some kind of consistency in the predictions, at least consistent. The prediction should be, or the model should be consistent with your priors, right? And that's, yeah, one of the aims is to improve extrapolation, for example, or generalization, and as Markus was mentioning, and the out of the distribution, no? Or if there is like a distribution shift, maybe since physics is in principle invariant, you want to incorporate some invariances to the models, right? But it's not as, a happy ending as it is, as it looks like, no? At least in most of the examples that we have so far, there is like a trade-off between consistency and accuracy, and very often you lose a bit of accuracy for the sake of consistency. So not necessarily you improve accuracy, but yeah, maybe it's just because we are looking at different, or not the right measure of measuring accuracy, right? Maybe we want to incorporate consistency as one more measure of accuracy, right? So it's it's a difficult arena, and very often you won't gain too much accuracy. but you at least enforce some consistency with prior knowledge, right? And yeah, it's consistency with one axis, and the other one is the, let's say, extrapolation. And sometimes, yeah, you improve the model's extrapolation capabilities by incorporating these physics constraints.
Yeah, thank you, Gustav. And
yeah, maybe I think one thing to add is maybe really the gaining of interpretability also. So, and I think this is so it's not a contradiction, I think, to the machine learning and the physics, but rather they can help each other. For example, for better understanding of unobserved processes. So if we basically have just the machine learning, then we are kind of, we don't know in which space we are actually too many degrees of freedom. But the physical skeleton of equations can give us some anchor points, and then can help us to actually learn something about the system, like these latent variables, latent processes. I think that's one of the key advantages in terms of scientific progress, that we can actually learn about processes without the rigidity of functional descriptions that are totally parameterized, but we can also have non-parametric approaches that are more free, and where we can actually get new insight while staying in a physical framework where the core physical laws that we know about are obeyed. I think that's, for me, one of the big points.
Yeah, okay. Thank you, Markus and Gustav. And in your view, how close are we to deploying explainable and causal AI systems for real-time decision-making in climate crisis scenarios like floods or drought-induced migration?
Yeah, well, there's progress. But we are not that yet. I think that most of the developments are at, I would say, at academic level. Some early warning systems, they are incorporating some AI, and there is this initiative of warning systems for all that, it has in one of the core pillars to incorporate data-driven technologies there. I think, and this is I think common to both talks. Any system should be actually aware of causality, and eventually being scrutinizable and accountable. And that's why we are trying to push this thing of causal inference or causal representation learning and effect estimation in these two examples that I show you on migrations and food insecurity. But still, I think that there's like, little steps towards the final goal. This is an unresolved problem. And yeah, we need to, to account for many confounders and many assumptions in the system, and a lot of in all the steps and all the bridges that Marcus showed, we have uncertainty, and this uncertainty gets accumulated and propagated. So it's a complicated but yeah, I think that in both we would agree that we do not only need AI in this realm, but for proper development and deployment of systems in early warning, but also causal AI. Right? It should be, we need this robust equitability, equitable, fair systems, right, and accountable overall. Right? In the end, it's a recommendation for a decision, and this decision is taken by humans. So yeah.
Yeah, thank you, Gustav. And the last question is, AI for Earth sciences is powerful, but data biases and regional disparities in satellite imagery can skew the results. How do you ensure fairness and robustness in global applications, especially in underrepresented regions?
Yeah, that's another challenging question. There are like a bunch of techniques, I think, in machine learning that we typically use and take it for granted, like data augmentation or domain adaptation methods, right? So you develop a model, and then eventually that model will be deployed elsewhere on a different time regimes, etc. These methods are really needed, and actually this speaks to what Marcus said on domain adaptation or out of the sample prediction. I think there is also a unique opportunity in this complex system that we are working on, which is about we are not only dealing with environmental data and either carbon fluxes or remote sensing images, but we are dealing with people, right? In the end, so working with this interconnected system forces to look at it like holistically, right? Like in complex systems theory, right? So we need to incorporate and explore regularities in space and time of many different variables, societal, economical, environmental data altogether. And this is, I think, one of the nice opportunities that we have with these multimodal foundation models. But they won't be nothing if we don't make this representation causal. Also, I think that there is a third opportunity that we are kind of missing or not really widely exploring, which is involving people in the decision, right? Putting the user or the decision maker or the stakeholders in the let's say in the loop, no, and the model design or model development. So this interaction with the final decisors, I think is important, no? As to make the decision robust, accountable, and then in the process of developing models, then we can learn something about what is going well, what should be corrected, or this kind of things. No? But still, I mean, as the previous question, this is still unresolved, and it's more a kind of a speculative research question so far, I think. I don't know, Marcus, probably you have another opinion, or?
No, I agree. I totally agree. I think one thing that one should really mention, I mean, the basis of everything is actually data and observations. And I think one could not emphasize enough, particularly in today's situation, also in the US, where, for example, Earth observations, weather and hydrological observations are really are threatened. But also we know that there's a lot of data, and if you're talking about societal data, that's in principle there, but it's not available. So it's really, I think the whole thing is kind of, that's also what this data-centric AI to some extent also emphasize. We need actually to push also to really how do you say in English? I don't know, to get the treasure of data everywhere, so that the data itself is becoming representative. And actually the Earth observation itself can actually help, because, for example, if you take geostationary data or geostationary satellite, they have the best data over Africa, so that's really nice. But other data, ground observation network, are actually pretty sparse. So we need to invest in this to have a more balanced observation system, actually. And I think that's not an AI thing only. AI can actually help for optimal design and so on, but it's actually a political question. And as a community of earth scientists, we should really strive for this more representative data, even if it's not always in front of our door. Basically, it's really important, I think.
Yes, and this is actually boiling down to the question of raising these concerns of biases, no? Because biases will propagate through all the models, and then that will kind of exacerbate more the differences, and then only the rich north will develop these vast and big models, and then not that much data is actually harvested from the global south, and it's kind of a feedback loop that it is actually aggravating the problems. No? So.
Yeah, thank you so much, Marcos and Gustavo, for presenting today and having this engaging discussion. And yeah, looking forward to the next AI for Good Molecules to Models webinar series, likely in autumn this year. We go ahead after the summer break. So thanks so much for presenting today, and see you soon.
Bye.
Thank you. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.